Okay. Last time we mentioned that the each component for the joint, like the bolt, the screw or member, the plates, can be regarded as a soft springs. Okay, so if they are the soft springs, that means we can define its stiffness, right? By spring constant. We can define them as spring constants, no matter it's the bolt, the nuts, or the members, right? This is what we already learned last time, right? Okay, so first let's focus on the bolt stiffness. Okay, so actually load rod partially threaded and partially unthreaded. Okay, so we can define a joint with the bolts, nuts, and the members with thread and unthread. Okay, thread and unthread. And each of them has its own stiffness, or we say it's the spring constant, K. Okay, spring constant K. So in this case, we define spring constant for the thread, partially thread spring constant KT, and unthreaded is KD. Okay, KT and KD. Okay, so maybe there's some text has been removed by this figure. Okay, but I'm gonna expand it. Okay, and we can consider each portion, each parts as a spring. Okay, as a spring, and then we can combine the thread and unthread it. Okay, okay, so we can combine two springs in series. Okay, so let's say the resultant equilibrium spring constant 1 over K equals to 1 over K1 plus 1 over K2. Okay, so we can just write it in the K equals to the K1, K2 over K1 plus K2. Okay, for thread and unthreaded. Okay, okay, so theoretically, we know the K, the spring constant, okay, equals to the area times the materials property, Young's modulus here, and the length, okay? The length, threaded and unthreaded. Threaded length and unthreaded length. Okay, okay. And then we can just plug these two values in the K. Okay, and then we get the KB. The B here represents the bolt, B-O-L-T, bolt. Okay, the stiffness of the bolt. Okay, equals to AD times the Young's modulus. Okay, so we just suppose the bolt is made of the the same materials. Okay, divided by the ADLT plus the AT times the LD. Okay. Okay, so here we define a parameter called the stress, tensile stress area AT, which is the area of an unthreaded rod with the same tensile strength as a threaded rod. Okay, so this is the cross section. Okay, we define it as the AT, the tensile stress area. Okay, so it can be roughly evaluated by this relation. Okay, the dP is the pitch diameter. Okay, and the dr is the root diameter. Okay, so the average of these two diameters squared times pi over 4. Okay, let's just estimate the stress, tensile stress equals to this. Okay, and also we can define the pitch diameter equals to D, the nominal diameter or the major diameter times the 0.65 times the pitch, and the dr equals to the nominal diameter minus the 1.23 times pitch. Okay, so this tensile stress area AT, it is the effective area of a threaded rod to be used for stress calculations. Okay, and the diameter of the unthreaded rod is the average of the pitch diameter and the minor diameter of the threaded rod. Okay. Okay. Okay, so there are some definitions for the bolt stiffness, how to find it. Okay. So we can look for some tables from our textbook to define the thickness of the washer and the knot thickness. Okay, and the grip length. Okay, the grip length. Okay, so for figure A, the L, the thickness of the old material squeezed between faces of the bolt and the face of the knot. Okay, and for the figure B, right? So for the figure A, these two member thickness are similar, right? So for the figure B, the T1 is much smaller than T2, right? Much smaller than T2. Okay, and for the figure A, these the threaded parts, the length of the partially threaded length is smaller than the unthreaded length. Okay, and for the figure B, right, these whole knots are threaded. Therefore, the grip length can be defined as what we already learned last time, right? Okay. Okay, so we can just check the fasten length. Okay, for the figure A, previous figure, where the L, what is L? Right here. Okay, the L is greater than the lowercase l plus h. Where's h? H is right here. The thickness of the knot, right? For the figure A. And for the figure B, the L here, the fasten length, that's being the part can be fixed, fastened together, can be gripped together. Okay, equals to h, the lowercase h, plus 1.5d, the nominal diameter. Okay, and this lowercase h here, which is the thickness of the washer and the member one, the first member. Okay, the T1, T1. Okay, okay, okay. And for the threaded length, LT, let's just look into the matrix units. Okay, so the LT equals to 2 times 2D plus 6. Okay, when the fastener length less than 125 millimeter and the major diameter is smaller than 48 millimeter. Okay, and with this threaded length LT equals to 2D plus 12 millimeter, when the L, okay, the L is the fastener length, is greater than 125 and smaller and equal to 200 millimeter. And when this threaded length is 2D plus 25 millimeter, when the fastener length is greater than 200 millimeter. Okay, so it's some design information. Okay. Okay, so the length of unthreaded portion in grip LD equals to the LL, the capital L minus the LT, right? The fastener length minus the threaded length. And the length of the threaded portion, LT, equals to L, the lowercase l minus LD. Okay. And this area of unthreaded portion, AD, equals to pi d squared over 4. Okay. And the area of the threaded portion is the AT, which is the tensile stress area, which can be found from the table, okay, the handbook table. We can find the tensile stress area, okay, and we already find the fastener thickness, right? KB, the B presents the bolt equals to, right? AD times the Young's modulus divided by ADLT plus ATLD. Okay. Okay, so let's look into the member stiffness. Previously, we defined the bolt stiffness. Now, what is the member stiffness? Okay, so we have to take into account the stress distribution spreads from face to bolt head and knot, right? And this model as a comb with top cut off called a frustum. Okay? Okay, so we have the member 1 and member 2. This is our knot, right? This is our bolt, and this is our knot. To fasten them together. Okay, so the previous slides, we defined the bolt stiffness KB, right? Now we have to define the member stiffness KM. Okay, so we can just define this stress distribution within the members as a frustum. Okay, it's a frustum like this, right? This is its stress distribution. As we model it. Okay, we cannot actually just see the stress distribution, but we can model it. Okay, we can model it. Okay. Okay, so the model compress the member as if they are fractals spreading from the bolt head and not to the midpoint of the grip. And each frustum has a half apex angle alpha, and you have to find the stiffness for frustum in compression. Okay, so this is the model. As I mentioned, this is just a model. We define it. Okay, by engineering point of view. Okay, so this is our boat, right? And this is the member. Okay, and this DW is the washer diameter, and the D is the major diameter of our boat. And this is the member. Okay, the member. Okay, so we suppose we model the stress distribution as a comb shape like this. It's a comb shape like this. Okay, so we can find the half apex angle, right? If we extend this, right? This stress distribution. Okay, so we can find this is the alpha, right? This is the half apex angle here. Okay, so from this triangle, anywhere from this triangle, we can just move it to here. Okay. Okay, and if we just separate this triangle into a small element with the thickness or with the with the thickness dx. Okay. Okay, and this small element thickness dx in this dark region, this black region here. Okay. Okay. And then let's look for this member stiffness. Okay, member stiffness. And the thickness is T, right? It's the member thickness, right? It's the member thickness. Okay, so we can define the deformation or deflection. D delta equals to P times dx over EA, right? I think you guys must learn this from your materials mechanics course, right? You remember delta equals to PL over AE, right? This is what we learned from the materials mechanics course. Okay, here the same thing, right? The boat is being stretched. Okay, the boat feel being stretched. Okay, and the member feel being compressed, right? So for this tensile elongation, the deformation, the delta equals to P, the X squeezing that small tiny element over EA. And the area of the element equals to pi times the, okay, R naught squared minus the Ri squared. The R naught represents the outer ring, outer ring radius, and Ri represents the inner ring radius. The inner ring radius. Okay, therefore, from this triangle, okay, right? From this triangle, any triangle, okay, doesn't matter, okay, okay, from this triangle, okay, so this is alpha, right? Okay, so we can define the R naught square equals to X times tangent tangent alpha plus 2 radius square. Okay, and Ri equals to D over 2 square, right? I think it's not difficult to understand, right? So can define each diameter here or here, right? Or here, right? Here. And this is the R naught. And here is the Ri, right? Okay. So we got this and we can rearrange this equation, right? We can rearrange this equation equals to this term. Okay, so as we already know the delta, the deformation or the deflection or the elongation, okay, equals to what? Here, right? Okay, so we can plug this area to here. And we take the integration. We take the integration to remove this the derivative sign, right? And with integration from 0 to t, the t represents the thickness of the member, right? Thickness of the member. Okay. Okay, so we can just play with this equation, right? So we can calculate it, right? So we will find this delta equals to this term, right? And the stiffness constant, or say the spring constant K equals to previously we already defined as the F over X, but in this case it's P over delta, right? P over delta, right? So we can remove this to the denominator and remove this term here. Okay, so we got the result is the member stiffness constant K equals to this ugly term, right? In fact, it's not ugly, it's quite symmetric, okay? But usually we won't use that so complicated equation, okay? Okay, so with the typical value of the alpha equals to 30 degree, right? So we can plug 30 degree here and here and here, right? Right? So we got this member stiffness. Okay, member stiffness. And we can plug this, or we can use this equation to find the stiffness for each frustum. And we can combine all frustums as the springs in series. That's mean if we have different members, we have the plate 1, plate 2, plate 3, and so on. Okay, and for example, the plate 1 can be made of wood. The plate 2 can be made of the steel. The third plate can be made of whatever, the nickel or copper, and so on. Okay, so we can find this member stiffness. The 1 over km equals to, right? It's like the resistance combination, right? The resistance in series. Okay, so we can get a reciprocal of the K1 and so on. Okay, and so on. And then we just rearrange this equation. Okay, and we get, okay, the Kn, right? So if the group consists of any number of members, all of the same materials, all the members, all the plates are made of, suppose like steel, okay, steel, and two identical frustum can be added in series, and the entire joint can be handled with one equation. So in this case, the members, all of them to be the same materials. Okay, so Km will equals to this. And the dW here is the watch face diameter. And the standard washer face diameter is roughly equals to the 1.5 times the nominal diameter. And with the alpha equal to 30 degree, we can just convert this Km, right, into this formula, okay, and into this formula, okay. Okay, so for the grade specified materials heat treatment transit, we can check the different tables in our textbook, and those grades should be marked on the head of the boat. Okay. Okay, so for this materials point of view, we have to look into for the boat, we have to look into the proof strength as the maximum load that a boat can withstand without acquiring a permanent set. Okay, the proof load. Okay, and for the proof strength is the curvature of the proof load and the tensile stress area. That's mean the proof load divided by the stress tensile stress area, which corresponding to the proportional limits. Okay, proportional limits. Okay, proportional limits, and slightly lower than the yielding stress, and typically used for the static strength for the boat. Okay, so for the boat design, we use the stress, which is the SP, which is the proof strength, okay, corresponding to the proportional limit, but not the yielding stress. Yielding stress. And remember that for the proof strength is typically being used for the static loading, but not the dynamic, but not the fatigue. Okay, and the good boat materials has a stress strength curve that continues to raise to fracture. That means it's not suddenly fractured. It's gradually and continuously to fracture. Okay, continues to fracture. Okay, there's an example of the grade both back. So we have the M is the metric SI unit, the nominal diameter. Oh, it can regard it as the major diameter if we define this tolerance is 0. Okay, and the P equal to 1.575 is the pitch diameter ISO standard, and the 4.8 the metric class with the type of the bolt, right? Hex head bolt. Okay. Okay, so there's some detail of this number. I'm gonna skip this, okay? But you can check the table, okay, here. Okay, you can check the table for the grade and this proof strength and the tensile strength and yielding strength corresponding to different head. Okay, the screw head. Okay, and okay, the same thing, you can define the class, right? In the previous case, it's 4.8, right? Therefore, we know, okay, the size range from M1.6 to M16. Its proof strength is about 310 megapar, and its tensile stress, minimum tensile stress is 420, and its yielding stress is 340. Okay, so in this head, we are marking the 4.8. Okay, we are marking the 4.8. Okay, so how to get those numbers? Okay, maybe I'm gonna skip this in this course. Okay, so you can just look for some handbook. There's a rule. There's a rule to define why is the class is 4.8 and whose proof strength is 310, and why the tensile stress is 420, and why the unit stress is 340. Okay, it's not randomly picked value. Okay, there's a spec rule for this class. Okay, for this property class. Okay, I'm gonna skip this topic here. Okay, but you can just simply check the table. Okay, just simply check the table. Okay, so next, we're gonna discuss what's this tension. Okay, we're gonna discuss what's the tension loaded bolted joint. Okay, so for the joint, the preload must be applied. Why? Because we fasten, right? We just fasten the bolt and nuts. But there must be a force to compress the member. To compress the member. That's the preload. Okay, that's the preload. And the P total, which is defines the total external tensile load applied to the joint. Okay, and the P is representing the external tensile load per bolt. And the PB is the portion of the external tensile taken by bolt. And the PM is the portion of the P taken by member. Okay, and the FB is the force, is the resultant bolt load equals to the FB, right? The FB plus the preload. And the member, the resultant load on member equals to the PM minus FI, the preload. Okay, so we can regard the P or P total, which is the force desired to separate the members. We're gonna break them apart, right? Therefore, the direction mass opposite to the preload. Okay, and then we define the C is the fraction of the external load P carried by bolt, and 1 minus C equals to the fraction of the external load P carried by member, and N equals to the member of bolts in joint. Okay, in joint. Okay, so in this case, the same thing. We have the bolt, right? So during the bolt preload, okay, the bolt is stretching, right? The bolt is still stretching, okay? And the member in grip are compressed. So the bolt stretch, the member compressed, right? Okay, so this is without preload Fi. I'm sorry, it's not correct. In this case, it's without the external load P. Okay, without external load P. So when this external load P is applied, so what's the situation there? The bolt stretch it further, right? Because we have the P, the force P desired to separates these two members. We're gonna break them apart, right? Therefore, the bolts, they will be stretched further. That's mean you have the addition amount of the deformation delta, right? Delta. Okay, we already have the tension applied to this bolt. Right now, when this extra external load apply, so this bolt itself must feel being stretched further, right? And the members in grip are uncompressed, the same amount of delta, right? The same amount. So this member, they feel not being compressed so much. Okay. 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 So we know the delta deformation equals to the force over the K, right? Okay. And the delta for the member is PM over KM, right? And we can rearrange the PM equals to PB times KN over KB, right? We can rearrange this PN. Okay. Okay. Since the P, what is the P? P is the external load, right? External load equal to PB plus PM. And the PB equals to KB times P over KB plus KN. Okay, we have the P, we have the PM, right? PM, we can plug the PM here. Okay, so we can find the PB. Okay, and we define a parameter C, right? Which is the terms of the KB over KB plus KM. And the PM equals to the P, the external load minus the PB equals to 1 minus C times the P. Okay, and here the C is defined as the stiffness constant of the joint. Okay. And the C indicates the proportion of the external load P. That's the bolt we are carrying. Okay. Okay. A good design target is around 0.2. C will equals to 0.2. Okay. Okay. Of course, we can check the table, right? Okay, we can check the table. With the stiffness different. Let me change the color. With the stiffness and the bolt grip, right? An inch, and the KB, KM, and C, and the 1 minus C. Okay. Okay. So for the resultant bolt load FB, this resultant load means we have to take into account the preload. The preload had to be considered. Okay, therefore the FB, the bolt force, resultant force, equals to the BP plus FI, right? The preload. Okay, this is the preload. Okay, it's the external force applied to the bolt, right? We are equals to the CP, right? Plus the FI, and the FM must be less than 0. Okay, less than 0. And the resultant load on member is resultant bolt is resultant member. Okay, equals to FM, right? Equals to PN minus FI equals to 1 minus C times the P minus FI. Okay, and both of this resultant bolt load or the resultant member load, the FM has to be smaller than 0. Why? And these results are only valid if the load on the members remain negative. That means That's the 0, indicating the members are still in compression, right? So if this Fm equals to 0, that means this members has been separated. This members has been taken apart. Okay. Okay, so the relating bolt torque to bolt tension, the best way to measure bolt load preload is by relating measure bolt elongation and calculated stiffness. Usually measure bolt elongation is not practical. Measuring applied torque is common using a torque wrench. Need to find relation between applied torque and the bolt preload. Okay, so this descriptions describe that. So for this preload, the elongation, okay, and the stiffness is not practical. That means it's useless. For the real case that we have to evaluate how much the force we have to apply to fasten the boat, right? It's not impractical. So what is the practical parameters that we're gonna use for evaluate, okay, how to tighten this boat? That is the torque, because we can simply use the torque wrench to define the torque. Okay. So we need to find a relation between the torque and F, the bolt force. Okay, so let's look into the torque right now. Okay, so for the Pascal equation that we already figured out, right? We got a T, the torque, right? Including the collar friction force. Okay, so here we just apply the tangent lambda equals L over pi dm, right? And then we assume the washer face diameter is about 1.5 D, and the collar diameter DC equals to the D plus 1.5 D divided by 2 is around 1.25 D. Therefore, we can rewrite this torque equation here. Okay, so remember the previous slide, I already mentioned what's this real case or the real relation we are going to figure out is the applied torque and the bolt preload, right? The bolt preload. Preload is the force that we're going to fasten, right? We're going to fasten. Okay, so we have the torque. After Fi is the preload, and the D, the diameter, the screw diameter, the nominal diameter. And then we can define a term in the brackets as the torque coefficient K. So what is the K? Here, right? It's the K. Right? So we can simply define the relation between the preload and the torque, right? Torque and the preload. And the K is the torque coefficient. Okay. Okay, so there are some recommended value for K. This K values as evaluate from terms of the experiment. Okay, terms of experiments, and we list the table for the each case, each condition, both condition corresponding to their K values. Okay, K values, and usually we define the K equals to 0.2. Okay, 0.2. Okay, and this if this K with the different condition, which have its corresponding K value. Okay, of course, if you're gonna develop a new uh, a new boat made of like, or I use the, for example, if I use the high entropy alloy to make a boat, and in this case, we have to define a new K value because no one used the high entropy alloy to make up the whole boat. Okay, so if in this case we have to define the K, we have to define the K, right? Okay, to define what is the K is. Okay. Okay. So okay, that means look into the other topic is related to safety factor, right? So we have to design a boat, right? Of course, we need a safety factor. Here, we're gonna only discuss about the static loading case. So we have to think of the yielding factor of the safety and the load factor and the joint separation vectors. Okay. Okay. So this NP, this yielding vector of safety, is against the static stress exceeding the proof strength. What is the proof strength? We already described, right? So if you still remember that, the proof strength SP is corresponding to the proportional limit, okay? To load a boat close to the proof strength, often not much greater than unity. Okay. The second factor is called the load factor. Okay, we're applying only to the load P, the external load, right? For overloading. Okay, that means we have a large external force applied to that joint. Okay, and how much the force can be, we have to define the load vector. Load vector. Okay, and the third is the separational vector. That's the external load is smaller than that need to cause the joint separation. Okay, so I define this N naught to specify the external load, which is smaller than that need to cause the joint separate. Okay, and if the separation occurs, the entire external load P equals to P naught. This separation joint separation vector times the P naught. Okay, will be imposed on the boat when this to cause this Fm, the member resultant equals to 0. Okay, and the P naught is the value of the external load caused during separation. Okay. Okay, so for the actual stresses for the boat, the B means boat stresses equals to the force divided by AT. AT is the tensile stress area, right? So from the previous slide, we already know the FB equals to CP plus the preload, right? And for the yielding vector of safety, the NP equals to the proportional limit, or let's say the proof strength divided by the sigma B, right? So we can just plug this number here, right? So we got this the yielding factor of safety. Okay. And for this okay, and for this load vector, okay, we can times the NL, the load vector, multiply the NL with the external load P, right? Because this the number NLP, this number must be larger than P. right? Much larger than P, right? So we can just times the NL, right? Times the NL here, okay? Okay, so we can get the NL, the load vector, right? The load vector. Okay. Okay, so that's mean how much the external force we're gonna apply. Okay, we're permitted to apply how much the external load P is permitted to apply. Okay, it's permitted to apply it. Okay, which can be defined by the load vector. Load vector. Okay, and for this joint separation vector, right? The P equals to N naught times the P naught, substituting in the Fm when to make the Fm equals to 0. Okay. Okay, so we can just plug this P naught equals to N naught P, right? So to here. Plug in here, and then we can figure out what is the N naught is, what's the N naught separation vector is. Okay. Okay, so recommended preload Fi can be roughly equals to the 0.75 FP for the non-permanent connection reuse fastener. And for the Fi is the 0.5 FP, which is used for the permanent connection. And this FP equals to the AT, the tensile stress area times the propulsion limit, or say the proof strength, okay, or say the proof strength. Okay, so I'm gonna stop here. Next discussion, we're gonna focus on the gasket joint. Okay, I have this members between the members. We just place the gasket in between. So how to evaluate the uh, the pressure? Okay, the pressure. Okay, and then we're gonna introduce the fatigue criteria for the fastener. Okay, fastener. Okay. Okay, so we're gonna stop here.